On November 7, 1940, a suspension bridge in Washington state began to oscillate in a 42-mile-per-hour wind. For 4 hours, the deck twisted and heaved. Then it came apart. The Tacoma Narrows Bridge collapse is one of the most filmed engineering disasters in history. It is also one of the most misexplained. What you learned about this bridge in physics class is almost certainly wrong. The standard story goes like this. The wind happened to blow at exactly the natural resonant frequency of the bridge. The bridge swung in sync with the wind. The oscillations built and built, like pushing a child on a swing, until the structure tore itself apart. This is called resonance. It is a real phenomenon, and it is not what happened at Tacoma Narrows. The problem with the resonance explanation is simple. Wind does not oscillate at a fixed frequency. Wind is turbulent. It contains a full spectrum of frequencies all at once. It cannot lock onto a single resonant frequency and pump energy into it. If resonance were the cause, then every bridge in every windstorm would be at risk of catastrophic failure. They are not. The Barker Committee, convened in 1941 to investigate the collapse, concluded that resonance was not the cause. Subsequent engineering research across the following decades confirmed this. The textbooks still got it wrong. Some still do. The actual cause was something called aeroelastic flutter. It is a different phenomenon, and understanding it requires looking at how the bridge was built. The Tacoma Narrows Bridge, designed by Leon Moisseiff, used a solid plate girder for its stiffening structure instead of an open deck truss. Most suspension bridges of the era used trusses, open lattice frameworks that let wind pass through. The plate girder was solid steel, 8 feet deep, running the full length of the bridge. It was elegant, it was economical, it acted like an airfoil. An airfoil generates lift when air flows across it. The angle at which the airfoil meets the oncoming air, the angle of attack, determines how much lift it generates. When the bridge deck twisted slightly in the wind, its angle of attack changed. This generated a twisting force. The twisting force increased the angle of attack further, which generated more twisting force. This is flutter, a self-reinforcing feedback loop between structural deformation and aerodynamic force. The structure's own motion changes the forces acting on it, which cause more motion, which change the forces further. Unlike resonance, flutter does not require a matching frequency. It generates its own. Once the flutter begins, it extracts energy from the wind continuously. The amplitude grows. The structure has no way to damp it. Eventually, the stresses exceed what the structure can bear. To understand why Moisseiff used a solid plate girder, you need to understand where bridge engineering stood in 1940. Leon Moisseiff was among the most respected bridge engineers in the United States. He had contributed to the design of the Manhattan Bridge and consulted on the Golden Gate Bridge. He was a pioneer in applying deflection theory to suspension bridge analysis, a mathematical approach that showed suspension bridges were actually stronger under load than classical theory predicted. His work allowed bridges to be built longer and thinner than anyone had previously dared. The Tacoma Narrows Bridge was the third longest suspension bridge in the world when it opened in July 1940. At a width-to-span ratio of 1:72, it was dramatically more slender than any bridge before it. From the beginning, construction workers noticed the deck swaying in the wind. They nicknamed it Galloping Gertie. The oscillations were considered a nuisance, not a danger. The State Highway Department hired Farquharson, a professor at the University of Washington, to study the motion and recommend fixes. His team was still working on wind deflectors when the bridge failed. On November 7, 1940, Leon Moisseiff was in New York. A 42-mile-per-hour wind had been steady over the Narrows since morning. By 10 a.m., the bridge was moving in its familiar heaving pattern, but something was different. The oscillation mode changed. Instead of heaving up and down uniformly across the span, the bridge began to twist. The two edges of the roadway were moving in opposite directions, one side going up while the other went down. This was the torsional flutter mode, and unlike the previous motion, it did not damp out. A professor of civil engineering, Farquharson himself, was on the bridge filming the event. He and a reporter abandoned their car when the tilt became too steep to stand on. The car remained. The bridge was filmed from the shore. At 11:10 a.m., the main span began to break apart. Large sections of the roadway fell into the Puget Sound. The suspension cables remained intact. The towers remained intact. The deck came apart in segments, falling 190 feet to the water. One animal was on the bridge during the collapse, a dog named Tubby, locked in a car. The owner attempted to rescue it, but could not approach due to the tilting deck. Tubby died. Every person who was on the bridge had already evacuated. The investigation that followed did not produce a simple answer. The Barker Committee's 1941 report correctly identified aerodynamic instability as the cause, but the full mechanics of aeroelastic flutter in bridge decks were not mathematically formalized until the work of Theodore von Karman and subsequent researchers in the 1950s and 1960s. What changed immediately was design practice. The Federal Works Agency issued guidance that all new suspension bridge designs must include aerodynamic analysis and wind tunnel testing. The requirement to use open deck trusses rather than solid plate girders was effectively established. Moisseiff's approach, vindicated for decades by deflection theory, was retired. The Tacoma Narrows replacement bridge, completed in 1950, used an open truss system. It has stood without incident for over 70 years. Moisseiff had not made a calculation error. His bridge satisfied every engineering requirement of its time. The failure revealed that those requirements were incomplete. The science of aerodynamics had not yet been applied to bridge decks in the way the collapse demanded. This is the hardest kind of engineering failure, not the failure of a calculation, but the failure of a category. An entire class of risk, aerodynamic instability of long-span bridges, had not been formalized enough to put into a specification. The Tacoma Narrows collapse did not fail the engineering knowledge of 1940. It defined the engineering knowledge of 1950. Every long-span bridge built since then has been wind tunnel tested. That is the bridge's real legacy.